Hello, this is a short movie which will provide instructions how to import data into Irena. We'll be importing various types of data using the different Irena importers which you can find. So let me first talk about the data which we're gonna have. First data set, which there are three data sets here in three different folders. This one, ASCII small angle scattering data. If you go inside and open it up, you will find out this is a 3 or 4 column data set where you have actually a Q, intensity, uncertainty. I assume this would be delta Q, but you can see there are only zeros in there. So this is a standard file format which you may get from some of the instruments and small angle scattering. Then we have another one which is the non-ASCII data. In this one here, if I open with a text editor, I need some kind of text editor. Someone give me a text editor. Text. We look at that, how it looks like, then you will see that it contains lots of other information. There are some other numbers here, but then at the end of the day you have two columns of data. You have a radius in this case, and then you have some kind of intensity. This is actually a pair distance distribution function from some other instrument. And then we have the last data set, which is a canSAS Nexus. I have a few of them here. canSAS Nexus is an HDF5 based data format which is intended for exchange of the data between different instruments, both small angle X-ray or small angle neutron instruments, and packages for data reduction and analysis. So here is an Igor Pro with loaded Irena, and without loaded Irena, let's load the Irena in. When you load the Irena, you will get a menu called SAS, which contains all of the calls to various sub-packages of Irena. And now we have a choice what to import. We can import here ASCII SAS data. This is small angle scattering ASCII data. These are other data which are non-ASCII. And this is the Nexus data. Then these XML data, I don't think anyone produces any more canSAS XML data, so this is probably obsolete by now. So let's first start with the ASCII small angle scattering data, the ones which are more likely you're going to need. Here is a screen of the importer. I'm going to just scale it up so you can see it easier. So this screen here, you fill up from the top to bottom. So let's start, we select the data path and we point ourselves to the small angle scattering data. Notice there's just one file here. What you want to do is select the file, you want to hit test and preview. These two commands can be also replaced by simply saying double-clicking the file. It does the same thing as test and preview. What it will do is it will check on how many columns it can find, and it found 4 columns, so you get four rows of checkboxes here. The code cannot figure out what is written in at each column. That's practically impossible. So in this case you have to go in and select what is you think that is, or you have to somehow figure it out. So it's X is Q, Y is intensity, dy is error or uncertainty. If there was a dx like here, but it's obviously you can see it's 0 all the time, so it's not very helpful. But if there was a meaningful dq, you can actually collect the dq. Now if you select at least q and intensity, at least these two, you can actually plot the data. If you plot the data, it will generate a plot of these. If you have an uncertainty, we'll add the uncertainties to it. So what you can see is you can actually see this is the q value, this is the intensity value, these are the data. And you can see there's a lot of points here at high Q which have a very large noise. This is a typical case where an instrument for powder diffraction or other types of measurements is used for small angle scattering data collection, or a software for that is used, and it basically generates a Q point for every pixel which that is as you walk away from the center to the outside. The result of which is you have lots and lots of points at high Q. The problem with fitting data like these is that these data there's a lots of points here which have very high uncertainties. They're going to swamp the fitting routines quite well, basically forcing the fitting routines to fit well this very noisy part of the data, often ignoring the low Q data, which is where most of the information is anyway. Notice that basically the code recognizes there's too many data points and it says consider reduction. The way you can reduce the points is we're going to process them down here, and I can show you where it is. The things which you now have to make a decision on also is if the Q is in inverse angstroms, which is how the Irena works. It uses inverse angstroms. If it's inverse nanometers. If you select a different checkbox, if you select the inverse nanometers, the Q will be converted on import to inverse angstroms. If there are many files in here which you need to somehow reduce the number of so you can actually work with it, there are various ways you can deal with it. You can put a data extension. So for example here, if you would put the data extension DAT, then of course there's no files with DAT. However, there is a file which TXT. Okay, so if you have many different types of files, you can scope it down and reduce it. The other thing which you can do, there's a match name string. So for example, if you just put here SAXS, then it will show only the files which contain a SAXS in the name. By combining the data extension and data names, the match string, you can reduce the number of data sets which you can see here, and hopefully extract the right or process the right data set. If you do not see the file in here which you are expecting, make sure that you remove the extension and you remove the match name string. This is the most common problem which I have with people, basically putting stuff in there and not realizing that they cannot see a data set afterwards. Keep in mind these things, at least the match name string is reliably a case specific, so you have to match the capital and lowercase letters correctly. So after you made a choice here, which files and what the Q value is, we have few other choices to do. Use file name as folder name is a most common way of importing the data. Basically, you're going to use the name of the file without the extension as a name for the folder. You can include the extension in the name, even though I have no idea why would you do that. Do not use USAX names unless you have slit smeared data and want to deal with that. So under basically no circumstances you should use USAX names. Use the QRS wave names. Do not use QIS since the NIST package is probably retired by now and very few of you are going to have any chance of using it, then this is not necessary. Auto override is if you're playing with the data, this will override the data without asking a question, just in case if they already exist in the Igor experiment. If you need to put data on a different scale, let's say on import, you want to convert the data from normalized to absolute scale, you can scale it here by checking this checkbox, and then you can scale it by a factor. So if you have a calibration factor which needs to be applied, you check this and this calibration factor goes here. You can slit smear the imported data, so in case you have a pinhole collimated data like here, but you would like to, for example, merge them with a slit smeared data which you exist, you can actually put a slit length in Q units here, and then you can slit smear the data on import. You can remove intensity less than 0, sometimes that is useful, because sometimes you can find out there's lots of points going to negative values, depends. You can trim the data, so in case you have bad points at the beginning, let's say some places do not mask the very low Q points which are behind the beam stop, and then you have zeros or very low intensities at first few Q points, that will cause lots of confusion. So you can, and sometimes they have high Q points which don't necessarily mean anything, because again they may be outside of the detector, but they exist at least in the data file. You can put trim data, and then if you change these zeros into some values, then it uses the Q this would be the minimum Q of the data, and that would be the maximum Q of the data. So you can trim the data. You can reduce the points. That's a useful thing to do. In this case, I would like to reduce it to 250 points, for example. And sometimes the input data are very, very long. Unluckily, Igor Pro has only 32 characters limit in the names for the folders, waves, and everything else. And on top of that, Irena and Nika need few characters here and there to deal with it, like assigning the proper names and so on, which you can actually see here. So this is a Q name, so it's Q underbar and a file name. So if this whole thing needs to be only 32 characters, then your file name can be only 30 characters or so. Actually, there's internally, I think, limited to like 26. So typically what happens, we truncate the end of long name. So if this name here of the file would be too long, after you reach 26 character or so, we just throw everything else away. Now that may not be good if most of the useful information is at the end, so you get other choices. You can truncate the start of the long name. If you do it, it will truncate the front and leave the end. You can also sometimes find out that your names contain sample Adam underbar measured on 25th January underbar, and then you may have some useful information. The remove string from name allows you to actually go in and remove the common name, a common part of the name, which is useless, because if you measured 50 times sample Adam, then probably want to call the Igor experiment sample Adam and not necessarily every subset of data. So you can play with this. If your data are on arbitrary scale, in other words, they are just normalized but not absolutely calibrated, then you keep it in calibration arbitrary. If they are in a standard centimeter square per centimeter cube per steradian, or centimeter minus 1 steradian minus 1, that would be a standard calibration, and this is a calibration per gram. These are important later on in Irena, so pick the right ones if you can. When you are happy with this will tell you where it's going to go, where the data are going to go. So it's going to, there is a root folder exists always. Irena will create a folder called SAS imported data file name. If you don't like this, you can simply change this into, for example, okay? And then it will append the file name, and inside there's going to be a wave Q underbar file name and so on, and this will contain your Q vector, intensity vector, error vector. It's also a hidden wave DQ, which is not shown here. That one has a W in front of it. Now what you do is you select the one or more files and you hit import. When you do it in the history area, you get a note. It says imported here from this file. Data are stored in this folder, and I created new waves and so on. So now you can go in and look in the data browser. If you do not see the data browser, you go to data and select data browser. In here you can then go, and in here we have a SAS, and in there we have a test SAXS, and in there we have a SAXS ASCII data, and we have a Q, which is a scattering vector, R, which is the intensity, S, which is the uncertainty, and W. That gets created even though you did not have it in your original data, because you were rebinning the data. When you rebin the data, the delta Q wave, which is W in this notation, gets created out of the width of the bins. Now, what happened as we did the rebinning of the data is we can look at the plotting tool and plot these data in a plotting tool, and when you do it, notice how many points you have here with 670, and there is a less points here. If you decide you want to reduce the number of points, I'm going to set it to auto override and reduce this one to 150. Oops, too many. Let's do 100 and import. If you look on that here, what happened, now it's obvious. You started with 650 points here. Out here you're representing the same curve by 100 points. The representation, the binning, is done on log scale, so there's as many as possible points preserved at low Q, and as you go to higher, more and more points are binned. So you can see they're on a log Q scale approximately the same width. This helps solving the numerical problems of the of the fitting of the data, because now across this data set it's much better weight. Also, the uncertainties at high angles are, there's not so many points with such a high uncertainty, but there's less smaller uncertainties. You can actually display them. If I can find it where it is, I can display the uncertainties. You can see that now lots of noisy points with higher uncertainties were averaged together, and you get a less points with smaller uncertainties, which is actually good for the fitting purposes. So now there was an import of the ASCII data. Now let me show you how the other data. So I killed all of these, and now I'm gonna go and try to import ASCII wide angle scattering or other data. These importers cannot run at the same time. You have to run one at a time. They use the same package, they're just different interfaces. I'm going to select a data path to non-SAS ASCII. I'm going to click here. I'm going to do a test and preview, or double click that, the same thing. Now, the Igor has a smart importer. It finds how many lines to skip, so you don't have to worry about these too many times. If there are more than one block of numbers, you may actually have to select skip lines and then basically remove some of the lines manually. Decide how many lines. For example, you could go in here and remove the first 28 lines. Now we have an X and Y. If you select X and Y, you can do plot. And here is a classical pair distance distribution function. Notice it jumps up and down to positive and negative values. Again, you need X units, either angstroms or inverse nanometers, inverse angstrom, inverse nanometers. And then out here we have a Q versus intensity, D, which is a D spacing, in which case the X unit is angstrom, or theta, which actually uses degrees for units. So this is a little bit awkward in cases of non-X-ray, non-SAXS data. Anyway, I should probably add in here a PDF type data anyway. You can also use a file name as folder name. It's basically the only choice here. You can scale imported data. You could remove the intensity less than 0, but that actually in cases of pair distance distribution is a really bad idea. It makes no sense. You can trim the data, so you can remove lower, smaller and higher points, and you have the same choices here with names. And then you can simply do this, and this is test non-SAXS. Okay, and then we just simply select it and import. When we do it, we can go and notice it's now in here. So in SAS, there's a test non-SAXS. There's a folder which has a name. Notice the name of the file was way too long, pair distance distribution measurement. So it actually cut it down to pair distance distribution MEAS, and that was enough because we need a Q and S. You could always create also a intensity uncertainty. Some of the tools may need it, so you can create a square root or you can create a percentages. So for example, in this case we could create something like 4% and then do an import, and then you have an uncertainty the same way as you have the pair distance distribution function. So that takes care of the data like powder diffraction data, pair distance distribution function, whatever else other types of raw data which are not necessarily small angle scattering data. Now the last tool which we have available, which I want to show you today, is the canSAS. So for some time a community of basically mostly beamline scientists and instrument scientists at large facilities has been developing a standard for writing data, 2D reduced data, in a Nexus file. The Nexus file is actually based on HDF5 standard. So it's a HDF5 defined container which then has a prescribed structure inside it, and therefore it's inside this big giant binary file. You can have one or more data sets which are now small angle scattering data sets. This should be actually very easy to deal with. You have again some choices how to limit this here, but if you select a file, you have few choices here. You can actually open the file in browser and look inside it, and this is an Igor HDF5 browser, and you can see that inside this file there is a structure where you have SAS data, SAS node, and it's actually quite interesting how it's written in here, but I don't expect users to need to know it. Okay, so I'm just going to close that. But what I'm saying is you can select this. There are various ways which you can name the files, and you may need to play with it. But basically I can select the file and hit import. When I do it, I'll get a folder called imported data, inside which is going to be, in this case we are using file name as a folder name, so it's a file name in here. Inside that one file name were 5 different data sets. You get TL, TL0, TL1, and so on. Now these are just named basically using the file name, but the advantage of Nexus file is they don't have to be that way. There is actually a string which contains a username, so I can actually name as a SAS entry as a username. When I do it, I will actually have other types of names. In this case they're not very helpful, they're workspace. So there's another type of names which is in there. Let's see if that one works, and that one may be the most useful one, because what you see is now, so the SAS title is now the proper name, and this depends on where your data come from. What did the instrument or the software which wrote the data did? How did they correctly name this? And this is basically a testing you cannot do. So in this case it says C4 SANS, so we measured the sample C4 on SANS, and we have a C4 SANS was measured second time, so if it already exists we'll just add a 0 to it, and you can see there's a G8 and G9. So obviously there are various ways to name the same data. So we always imported the same 5 or so data sets, but we gave them names based on a different structure inside. And as I said, once you figure out which names inside the Nexus file is what you want, you should know about, which one is the right choice here. You can include in a wave notes. In the wave notes are in Igor Pro. These, if you click in here and hit info, there's various information in it. Irena will put lots of information in wave notes. SAS instrument, SAS sample, and SAS node are different blocks of data which are associated with inside this file with your data, and they contain typically instrument metadata, things like wavelengths, distances, temperatures, and lots of other information. If you need to have those, you may want to include those, then they'll get written in the wave note and you can always get to them. So at this moment, then we could go in, we can pick a plotting tool, and then we have lots of these. So for example, here is a glassy carbon C4 measured on whatever SANS instrument that was, and you can see that it was relatively easy to get inside. So there are 3 different importers which you can use and typically will use, which I showed you. It was the ASCII for SAXS data, or SAS data, SAXS or SANS, ASCII for other types of data like wide-angle scattering PDF, Nexus, canSAS. Keep in mind it has to be canSAS. That's a standard how the 1D data are written inside the Nexus file. There is lots of other Nexus files which may not be canSAS data. I do not have handy example of XML data, so I'm not going to do that now. So this is all how to get the imported data in Irena, and then you can use them with the other Irena tools.